Good evening. I am Divyansh Tiwari, and today our big data team, a final project group that includes Vidya Sagar, Sai Akshat Rohit, and myself, are here today to explain a final project of big data. In this project, we have used the data set of Airbnb, which includes tremendous amount of data, starting from the host verification, host ID, the links, the location, the latitude, longitude, neighborhood of the Airbnb from Amsterdam, to the days, the places available, and the price per night, price per week, and the kind of facilities that they provide. Um, to begin with, we imported the libraries um, such as Seaborn, Pandas, Matplotlib, NumPy, and further more libraries such as pipeline, correlation, bucketizer, linear regression, random forest regressor. These all are used either to portray or depict what kind of data are we dealing with, or to build a model. Here, we loaded the data from the Databricks. We uploaded the data file, CSV file into the Databricks, and we write the file from here. Firstly, we try to visualize the data to have a better understanding of what we're dealing with. So these are the listings by the neighborhood we selected. Or the These are the neighborhoods, and apparently Debarges has the maximum number of Airbnb listings, which is approximately 3,500, and which goes on decreasing as the neighborhood goes out of the as the neighborhood is farther from the city center. By the property type, the maximum number of listings are apartments, and the least number of listings are loft. So it appears that the people who own the apartment or who have an extra apartment, they try to lease out, they try to give it out to as Airbnb more often than compared to house and townhouse. Listings by room. The entire room and apartment are the most common ones in the entire listing as compared to shared and hotel room. Um, Most of the apartment or the rooms that are being listed on the Airbnb accommodates to which is more than 10,000 of those. There are maximum one bathrooms in the listings. However, there are some listings have three bathrooms as well. And same is the case with the bedrooms as well. Most of the listings have one bedroom, and some of the listings, approximately 5,000, have the two bedroom, and approximately 2,000 have three bedrooms. As as the data says, the most of the uh, listings have one bed, followed by the two beds, three beds, and further. From the CSV file, we plotted the whole starting month, and it seems that the seventh month, which is July, is the month where most of the host gets on board with the Airbnb and roll out the listings on the website, whereas the first and last month of the year, which is December and January, are the months in which the least amount of hosts get on board with the Airbnb. From here, um, my friend Sai Akshat will take over, and he'll be talking about deriving new columns. Thank you.
This is Sakshit. Yeah. The next thing in our exploration is deriving new columns. So the thing which we have done is there's a column named amenities, which has like all amenities offered by a host, and we could see like on an average each listing has like around 15 to 20 amenities. So the thing which we are trying to do is that we could explore like what type of amenities are like most repetitive in our data set. So basically, the first thing which we have done is considering both cable TV and TV as a similar one, and we have done some data cleaning part, and thus arrived like which what are the top five amenities that which are like most frequent amenities which are being repeated in our, and we could see that Wi-Fi is the first amenity which is being most repetitive one, followed by heating, then essentials and kitchen and smoke detector. So the main reason why we have done this is whether these top five amenities would affect our price or not. And suppose if a customer wants Wi-Fi as his amenity, so how much he needs to pay extra. Or suppose a customer wants kitchen as his amenity, so how much he needs to pay extra. So this is the reason why we have considered these five amenities, and based on that we have considered a new binary column named as Wi-Fi, heating essential, and kitchen and smoke detector. And suppose a listing has Wi-Fi in its listing, then the Wi-Fi column will become one. And suppose if a listing doesn't have a Wi-Fi, then it gets a value of zero. And the similar concept is being applied for all five listings, sorry, all five columns. And these are the things which we have done for these new five derived columns. So the other thing which we were trying to explore is whether the distance from the airport and the distance from city center would affect our price or not. Generally, in any city, if a listing is close to some international airport or something, then the price would be a higher. And the other thing, why we have chosen city center is a city center is a like main spot for the most of the tourists. So it is like a tourist spot in city of Amsterdam. So we were also finding whether this would affect our price or not. And fortunately, if we go down to the we have done our correlation matrix, where we have got a, like, if you could see correlation of price and correlation of price with respect to airport and city center were negative, so which were indicating that whenever a listing goes is a far distance from an airport or city center, then our price would decrease. So that's the reason why we have included a new column called airport and city center. Basically, what we have done is here we have done a code which we have collected from some Stack Overflow and as well as some few other sources, and have done this code. And basically, it takes a lot of time to run. So, like we have saved this data frame once it is established, so that we could grab it from our HDFS whenever we require. So this is the other part. And these are the like five new derived columns which we have done for our analysis, and whether these five would affect our price or not. And now my friend Rohit will continue.
Hi, I'm Surya and I'll be explaining the data cleaning and modeling part of the project. Firstly, we have 20,000 records in our data set. These are all the variables for data set. Here now we're only selecting the relevant columns that we think will influence the price of a listing. We have considered around 25 variables, which include accommodate, bathroom, bedrooms, etc. Then I have converted all the data types of the integer variables from string to int or double. As you can see, some of the variables were having string as a data type, so I've converted that data type to either int or double. And then here I'm trying to find out the number of nulls in each columns. As you can see, security deposit and cleaning fee, these variables have around 10,000 null values combined. So I'm not selecting these two variables into my data frame. I'm removing them, I'm dropping them. And then here I'm trying to find the outliers for the price variable. So normally outliers are those which fall 1.5 times outside the interquartile range. So here I'm trying to find the bounds. I'm trying to find the Q1 and Q3, the interquartile range, and then I'm finding the bounds which is 1.5 times the interquartile range. And my max range is this is what I got, which is 314. So based on this, all the prices that fall after 314 are considered outliers for my distribution. So and again I've used bucketizer to see how many values fall inside 314 and how many are there outside of 314. So most of my values fall inside here, so we don't have any problem while removing this. We'll not have any problem if we remove this. So I'm just considering the prices which have less than 314 euros, so that we can build a better model, and we can our model will be better in detecting the prices which have less than 314. Now I have dropped all the values which have NA. This means any column that has an NA value will be dropped. The entire row will be dropped here. Now I just have 18,614 rows left. These are my descriptive statistics, the main median of all the integer variables, independent variables. Here I've found the correlation of my independent variables with price. The accommodates, bathrooms, bedrooms, and beds have the highest influence on price. The correlation for these variables is around 0.4, 0.3, 0.4. And again here, the correlation is negative for airport and city center, which means that as the listing moves away from airport and city center, the price is inversely proportional with the distance of airport and city center. As the listing is moves away from airport and city center, the price of the listing reduces. This is for the correlation plot. Again, this is the same. This is just a graphical representation of the correlation to see if we have any interdependencies. Now I'm creating a new column, log of price, because my price is not following a normal distribution. As you can see, it is slightly skewed to the right, but when I take the log of price, it is more a normal distribution. So it is better to consider log of price as my dependent variable. That way our normality assumption will be good, and our model will be better than it will be better when we consider only price. Log of price model will be better than price, because this is slightly skewed and this is normal. So here I have derived a new column, log of price, which has the log of the price value in that. This is my linear regression model. I am dividing the data into train and test with 70 and 30% respectively, and I'm converting all my categorical variables using indexer. And this is an important variable. We found that this has influence after some trial and errors, because a superhost is someone who is like verified by Airbnb, and he has an option on top of him. So this will definitely influence the price. And then I'm giving all my independent variables into my assembler, and the output will be features. Then I'm passing all the indexers and my assembler into pipeline, and then fitting the pipe with my train data, and then I'm transforming it. Then I'm plotting my log of price and prediction. This is the output. Now these are the residuals. This is the RMSE of our model. Now, as we have taken the log of price as the dependent variable, so for price, the root mean square error will be the exponential of this value, which is 15%, and the R2 value is 38%. It is 39%, which means the independent variables that we have considered are able to explain 40% of the price, which is not bad. Now let us see the coefficients. These are all the coefficients of our independent variables. This is the intercept. Now from here, what we wanted to explain is that we have a derived columns. We have some derived columns such as Wi-Fi, Wi-Fi, heating, etc. So from the coefficient for Wi-Fi, what we can interpret is that if a customer needs Wi-Fi as an amenity, then the price of the listing will be 2.5% more than a listing that does not have Wi-Fi as an amenity. and the same, and for other amenities, such as if the customer needs heating as an amenity, then he has to pay 4.7% extra than a listing that does not have heating option. This is our plot. It is not so good, but it is not bad as well. This is the actual versus predicted output. And then we have used random forest regression model, which is a bagging model, which basically is a combination of a lot of decision trees, hoping that it would explain our model a little bit better. So for the regression, the whole process is the same thing. I've used the same indexer and assembler that I've created for the regression model, and I've sent those to my pipeline here, and then transforming and fitting it is the same procedure as a linear regression. It's just that we have a different model object. Here we have random forest regressor, and here I've used max bins because some of my variables, normally the default setting is 32 for random forest regressor, the bins, but since for some independent variables I have more than 32 categories for the category of variables, so I have increased it to 500. And as to our expectation, this has the random forest regressor has done better than linear regression. Here we got an output of 44%. So in this model is saying our independent variables are explaining 44% of variance of price, and this is the plot of actual versus prediction for the log price, and this is about the models. Next, my friend Sagar will continue a model based on text analytics.
Hi, continuing from where my teammates have left off. So we also tried to use the textual feature of this dataset and try to get better predictions if possible. And to that extent, we have used the description column, which had the textual information. It is a description about each listing and how the listing is advertised in the website. So we try to do the basic cleaning again, the same thing that we have done in the previous models on the non-text data. And then we try to pre-process the textual data. So the textual data was pre-processed using the tokenizer stopwords remover from Pyspark library and the snowball stemmer from NLTK. We also use the regex functions. So the textual data was tokenized, and then the stopwords were removed, and then the stemming was done so that we get the canonical form of the words. And further, we filtered out the words which were less than the length of 3. So once we did that, you could see how the words were listed under a column. The words were captured in a list. So all the words that were relevant to this particular description were kept here. Further, we split the data into train and test with 80-20 split, and also did a seed so that we have repeatability of the results. Once the text data was cleaned and the words were extracted, we tried doing the vectorization and extracting the features from the text and numeric data. For that purpose, we have used TF-IDF methodology. So hashing TF and IDF from the Pyspark and vector assembler and string indexer were used for this purpose. So we converted the words into TF-IDF and this categorical words into indexes or the numeric data, and then use the vector assembler to convert them into features. So this was used to transform the train and test data. Further, we have conducted linear regression, the same thing that we have conducted previously without the text data, so that we have comparability. So the linear regression was run on the price as the target variable, and features were taken as the dependent variables. And the same thing was used to check the results on the test data. So we can see the predictions that were made using this model. They were slightly off, but I think we did a better a better outcome from this particular analysis using the text data. So you can see that from the RMSE and the R square. So the RMSE of 110 suggests that the predictions of prices was off by $110 on an average, and the R square of almost 50% suggests that the variation in the price was explained almost half the time. So this also gave us scope for further analysis. So we understand that the text data definitely has significance in the price variation of Airbnb Amsterdam dataset. So we can further improve this by doing some transformations on the variables. For example, we haven't done the transformations that we have done previously on non-textual data analysis, where we have used the derived columns of airport distance and city center distance, which we haven't used here, and also did not transform the target variable price as a log function, which we have done in the previous non-textual analysis. Some of the challenges we faced using textual data for analysis is understanding how tokenization, vectorization, and the stemming works in Pyspark library. So this has been a good learning, and I think we are now confident of using Pyspark for further analysis on textual as well as the numerical data. So hope you have liked our presentation. Thank you.